everyone. Today we will discuss something about the oscillation and simple harmonic motion. So, a motion which repeats after a regular interval of time is called as periodic motion. And if a body in periodic motion executes to and fro motion about a fixed reference point, then it is said to be having a oscillatory motion. In linear motion, we have some parameters like velocity, distance, displacement, speed, acceleration, etc. Similarly, here in oscillatory motion, we have some parameters. So we will discuss one by one. The first one is displacement. So in linear motion, displacement is nothing but when a body moves from one point to the other point, the shortest distance between those two points is said to be displacement. But here in oscillatory motion, this is called as the distance of a particle measured along the path of the motion from its mean position at a given instant of time. So here we are measuring the displacement along the path from the motion of its mean position. It is represented by x. Next one is amplitude. So amplitude is nothing but the maximum displacement of a body on either side of its mean position. Mean position is nothing but the position where the particle will be at rest. The next one is oscillation. Oscillation is one complete to and fro motion of the particle about its mean position. So it has to complete one complete to and fro motion. It has to come back to the same point. Then it is said to be one oscillation. Then comes the time period. Time period is the time taken by the particle for one complete oscillation. And frequency is nothing but the number of oscillations completed in 1 second. So it is the inverse of the time period. Then phase and phase differences. So the phase of a physical quantity which signifies the state of the motion of the particle executing simple harmonic motion. It describes the position and direction of the particle. So if you know the phase between two motion, then you can tell how one particle is lagging behind the other, or in other terms how the other particle is ahead of the first particle. So these are the some parameters related to oscillatory motion. Now we will move to the simple harmonic motion. Here one of the important term is the restoring force, means a force is acting on a body. The definition of simple harmonic motion is it is an oscillatory motion in which the acceleration or restoring force is directly proportional to the displacement but in the opposite direction. So as the displacement is increasing, there will be a restoring force which is acting on a body is also increasing, but it always tries the body to come back. So some of the characteristic of simple harmonic motion are the motion must be a periodic motion. It has to repeat after each in or particular interval of time. The time interval is called as time period. And next one is the force causing the motion is directed towards the equilibrium position. So the force is always directed towards the equilibrium position. The restoring force is directly proportional to the displacement. The next one is period of each cycle must be constant, or in terms of frequency, the frequency must be constant. Then comes the acceleration of the body must be directly proportional to the displacement but in the opposite direction. These are some of the characteristics of simple harmonic motion. Now, some of the example for simple harmonic motion are, you can tell this simple pendulum. Simple pendulum, swinging simple pendulum is example for simple harmonic motion. Then any spiral spring with the mass. If you stretch the mass, it will execute a simple harmonic motion. And then any stretched wire, if you pluck it, then it will execute a simple harmonic motion. You can give the example of guitar. We will derive an expression for differential equation of a motion for a body which is executing simple harmonic motion. So by this particular equation, we can find the position of a body at any instant of time. So now we will consider a body which is executing a simple harmonic motion. Let the mass of the body be small m, and let us consider that it has displaced by a distance of x at a time t. Now from the definition of the simple harmonic motion, we can tell that there is a restoring force F which is acting on a particle. The restoring force is directly proportional to the displacement but in the opposite direction. So we can write F is directly proportional to minus x, where minus represents the direction of force and x will be the displacement. To remove this particular proportional, we will introduce a proportionality constant K. This proportionality constant is called as force constant, stiffness constant, or spring constant. And the negative sign indicates the direction of the force. By rearranging the equation number 1, we can write K equal to F by X. So we can define force constant as the restoring force F per unit displacement. So the unit of this force constant K will be Newton per meter. Now according to Newton's second law of motion, we can write force equal to mass into acceleration. So m will be the mass of the body and a will be the acceleration of the body. We also can write acceleration as d square x by dt square. So we will write F equal to m into d square x by dt square. Now these are the expression for force, equation number 1 and 2. Now we will equate equation number 1 and 2. So we have m into d square x by dt square equal to minus k into x. If we rearrange this term equation, we will get at the end as d square x by dt square plus k by m into x will be equal to 0. But we have k by m as omega square, where omega is angular frequency. So we will get d square x by dt square plus omega square into x equal to 0. So this is a second order differential equation and is also a differential equation of motion for a simple harmonic motion. So the second order differential equation will have two sets of solution. These solutions will give us the displacement of a body at any instant of time. So we will see what are the solutions for these differential equations. If we solve the second order differential equation, we will get various sets of solution. It can have any form, but here we will get in the sine and cosine form. So the first set is x equal to a sine omega t plus phi, where phi is phase constant. And the second set is x equal to a cos omega t plus phi. And it can be also represented in exponential form, where x equal to a into e exponential of I omega t plus phi, where I will be the imaginary value. So here omega is nothing but angular frequency, a is nothing but the amplitude. So this covers the small part of simple harmonic motion. I hope you have understood whatever I have covered. Thank you for watching.